Picture this. You're standing outside on a clear night. You look up, you see a star. That light left its source before your grandparents were born, before their grandparents were born, before the pyramids were built, before Homo sapiens drew the first cave painting. That light has been traveling for thousands of years, and it just now, right now, in this exact moment, touched your eye. That's astonishing, right? But here's what nobody tells you. There are stars out there whose light will never reach you. Not because they're too far. Not because we don't have good enough telescopes. But because the universe itself, the fabric of space and time, is physically, mathematically, cosmically running away from us faster than light can chase it. And there is a wall. An invisible, absolute, terrifying wall at the edge of what we can ever reach. Not just with our rockets, not just with our bodies, but with anything we could ever build or send or imagine. And today, I'm going to take you to that wall. I'm going to show you exactly where it is, exactly why it exists, and exactly what it means for the fate of every human being who will ever live. By the end of this video, you will never look at the night sky the same way again. The universe you thought you lived in, the one that feels vast but reachable, the one that feels like it's waiting for us to explore it, that universe doesn't exist. And the real one is both more terrifying and more beautiful than anything science fiction ever imagined. Stay with me. This is going to take a while, and every single minute is worth it. If you're new here, welcome. Hit that subscribe button right now, because this channel is where we take the biggest questions the universe has ever asked, and we sit with them, wrestle with them, and refuse to look away. And like the video if this kind of thing makes you feel alive, because it absolutely should. Now I don't know something. Drop it in the comments right now. What country are you watching from? And what time is it where you are? Because I genuinely love knowing that somewhere. Maybe it's 2 a.m. and you can't sleep. Or maybe it's a Sunday afternoon and you've got a coffee in your hand. And across the planet, hundreds of thousands of people are all staring at this same sky together, through this screen, through this question. Tell me where you are. I read every single one. Now, let's go. Let me start with a number, not a metaphor, an actual number. 46.5 billion light years. That is the radius of what scientists call the observable universe, the sphere of space centered on Earth, from which light has had enough time since the Big Bang to reach us. 46.5 billion light years in every direction. That's the universe we can see. Now here's the first thing that should immediately break your brain. The universe is only 13.8 billion years old. So how can light from 46.5 billion light years away have reached us in 13.8 billion years? Light travels at the speed of light. That should be impossible, shouldn't it? This is your first hint that the universe doesn't play by the rules you think it plays by. The answer is expansion. While that light was traveling toward us, the space it was traveling through was stretching. Imagine you're an ant walking across a rubber band. Someone is pulling the rubber band as you walk. The distance you cover isn't just your footsteps. It's your footsteps plus the stretching. The light that started 13.8 billion light years away traveled through space that was simultaneously stretching away from it. And the combined result is that the light's origin point is now 46.5 billion light years from us. Think of it like this. Think of it like a treadmill. Light is walking forward on this treadmill, but the treadmill is also moving. Depending on how fast the treadmill moves, the walker makes progress, loses ground, or stays exactly in place. In the very early universe, the expansion was slowing down, so light could make net progress. But now, the treadmill is speeding up. This is the discovery that changed everything. In 1998, two independent teams of astrophysicists, one led by Saul Perlmutter, one led by Brian Schmidt and Adam Riss, were both studying Type Ia supernova, these exploding stars that always explode with the same intrinsic brightness, which makes them perfect cosmic measuring sticks. They were expecting to confirm that the expansion of the universe was slowing down due to gravity. Every physicist expected this. Every model predicted this. It was the safe, sensible, gravitationally obvious answer. Instead, they found that the expansion was speeding up. The universe is not just expanding, it is accelerating. Something is pushing space apart faster and faster with every passing moment. We have no idea what this something is. We called it dark energy because we have absolutely no idea what's doing this. Doesn't fit on a research paper. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011 for this discovery. And it is, without exaggeration, one of the most disturbing things science has ever found. Because here's what it means. It means the wall isn't stationary. The wall isn't just out there at some fixed distance. It's closing in on us. Right now, as you watch this video, the observable universe is the full 46.5 billion light-year sphere I mentioned. But the reachable universe, the part we could physically get to, the part where if we launched a rocket today and kept accelerating indefinitely, we could eventually arrive, that's much smaller. Scientists call this the Hubble volume, or more precisely, the cosmic event horizon. And it sits at roughly 16 billion light-years from us right now. Everything beyond 16 billion light-years? The space between us and any object that far away is already expanding faster than light. Any signal we send, any ship we launch, anything we could ever imagine dispatching in that direction will never get there. Not because of anything wrong with the ship. Not because we're not going fast enough, but because space itself between us and that destination is growing at a rate faster than light can cross. The destination is running away faster than any possible chase. And here's the part that should really keep you up at night. That 16 billion light-year horizon, it's shrinking. As the universe accelerates, more and more galaxies are slipping over that horizon, becoming unreachable. Galaxies that are reachable today will become unreachable in 1 billion years. In roughly 150 billion years, scientists estimate that our local group of gravitationally bound galaxies will be the only thing left visible in the sky. Everything else will have crossed the horizon. Everything else will be gone, not destroyed, just forever unreachable, forever invisible, forever gone from any possible experience or interaction. Think about that. In the sufficiently deep future, intelligent beings, if any exist, will look up at their night sky and see almost nothing. They will have no evidence that there was ever anything out there. They will have no way of knowing that their entire observable universe was once filled with 2 trillion galaxies. 2 trillion galaxies. Gone. Not with a bang. Just over the edge. We are living in the golden age of the universe's visibility. Right now is the best possible moment in all of cosmic history to be an astronomer. And it will only get worse from here. But wait, I said the wall is at 16 billion light-years, and I said it's the farthest we can ever travel. But come on, 16 billion light-years? We haven't even left our own solar system with a crewed mission. We haven't been back to the moon in over 50 years. We are cosmically, comically, almost insultingly close to home. So what do I mean by the farthest we'll ever travel? Here's what I mean. The question of how far humanity travels is not just a question of rockets and fuel and generations-long voyages. It's a question of what is physically possible within the laws of reality. And what I want to show you over the next 3.5 hours is the full architecture of those limits, from the practical to the relativistic, to the cosmological, to the thermodynamic, and why, taken together, they paint a picture of a universe that is strangely, beautifully, heartbreakingly finite in what it allows. We're going to start with the universe's speed limit. Then we're going to talk about what happens if you try to cheat it. Then we're going to go to the edge of the galaxy, then to the nearest stars, and beyond them. And we're going to encounter every wall in sequence. And each wall is going to be more interesting, more profound, more philosophically loaded than the last. But here's the cliffhanger I want you to hold right now, because we're going to come back to it later. That 16 billion light-year cosmic event horizon, the wall that marks the farthest we could ever reach, it is not empty space. It contains roughly 3 million galaxies, 3 million entire galaxies, that are, in principle, still reachable. And that number dwarfs everything humanity has ever explored by a factor so large it doesn't have a name. And yet, compared to the full 2 trillion galaxies in the observable universe, it is a rounding error. We are already confined to an island. The question is just how big the island is. Let's build the foundation. Let's start with light. Here's a question that sounds simple, but contains multitudes. Why can't anything travel faster than light? Most people have heard that this is impossible. Most people accept it the way they accept, don't stick a fork in an outlet. You don't need to understand the full physics. You just know it's a rule. But understanding why this limit exists, understanding it at a deep level, will completely transform how you see the universe and how you understand every barrier to travel we're going to discuss. Let's start with what Einstein actually showed us. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers in a single year, any one of which would have made him famous. One of them was special relativity. And what Einstein showed was not just that nothing can go faster than light. He showed something far more fundamental. The speed of light is not a property of light. It is a property of space-time itself. Let me say that again, because it's going to matter enormously. The speed of light, 299,792,458 meters per second, is not the speed of photons. Photons happen to travel at that speed because they have no mass. But the number itself is the conversion factor between space and time. It is the rate at which the universe converts one into the other. It is baked into the architecture of reality so deeply that calling it a speed limit is almost misleading. It's not a limit in the sense of a rule someone posted. It's a limit in the sense that a triangle can't have 4 sides. Here's how to really feel this. Think of it like this. Think of it like every object in the universe is always traveling through space-time at exactly the speed of light. Always, constantly, no exceptions. But the speed is split between motion through space and motion through time. If you're sitting perfectly still in space, all your space-time velocity is going through time. You're aging at maximum rate, experiencing time as fast as it flows. If you start moving through space, some of that space-time velocity shifts from time to space. You're moving faster through space, but slower through time. Slower aging. This is time dilation, not science fiction. It's measured in GPS satellites every single day, which have to have their clocks corrected because they're moving through space at orbital speeds, and therefore moving through time slightly slower than clocks on the ground. And here's the kicker. To reach the speed of light in space, you would have to divert all of your space-time velocity into the spatial direction. 0 motion through time. Which means time would stop for you. Which means you could not experience anything. Which means you would not exist, in any meaningful sense, as a being having experiences. To be at the speed of light is to be frozen in time. To be a photon that experiences no time between emission and absorption. To be something rather than someone. Massless particles like photons can do this. Anything with mass, anything that has the property of being something rather than just carrying energy, cannot. To push a massive object to the speed of light would require infinite energy. Not a lot of energy. Infinite energy. And infinity is not a big number. It is not a number you can reach by building a bigger reactor. Infinity means structurally impossible. But here's where it gets interesting, and here's where a lot of people stop thinking carefully. The speed of light limit does not mean interstellar travel is practically impossible. It means it's practically very, very, very hard. It doesn't mean the universe is closed off. It means it's far away. There's a difference. And for a while, For the next few sections, I want you to hold that distinction, because the wall that actually seals humanity's fate is not this one. This is the first wall. There are others, and the later ones are the ones that are truly absolute. Let me show you what relativistic travel actually looks like, because this is where the physics becomes extraordinary. If you launched a spacecraft and accelerated it continuously at 1 gram, that's the same gravitational pull you feel standing on Earth right now, which happens to be the most comfortable long-term acceleration for human bodies. Here is what happens. After 1 year of ship time, you're moving at 77% the speed of light. After 2 years of ship time, you're at 94%. After 3 years, 98%. The numbers are asymptotic. You get closer and closer to light speed, but never reach it, which is consistent with everything Einstein told us. But here's the astonishing part. Time dilation is working in your favor. Because you're moving so fast, time on the ship is passing slower than time back on Earth, and the difference becomes staggering. After just 10 years of ship time at 1 gram acceleration and deceleration, you could have crossed the entire Milky Way galaxy, 100,000 light years. Back on Earth, 100,000 years would have passed, but on the ship, 10 years. Your body aged 10 years. Think of it like this. Think of it like time is a currency, and the faster you move through space, the less of it you spend. A relativistic traveler is not cheating Einstein's speed limit. They're using it. They're exploiting the space-time geometry that makes the speed of light what it is. And the universe actually bends over backwards to accommodate them. The faster they go, the less time they experience crossing any given distance. In principle, a human with a very good spaceship could cross the observable universe in a single human lifetime. They would arrive to find the universe aged by billions of years. Everyone they ever knew would be dead, along with every civilization that existed when they left. But they would arrive. They would make it. This is the door that Einstein left open, and it's the door that everything else we're about to discuss is slowly, inexorably, permanently closing. Because remember that accelerating universe? That cosmic event horizon? That wall at 16 billion light years? Time dilation doesn't help you there. You can experience subjectively short trips to distant galaxies, but only to galaxies you can currently reach. You cannot use time dilation to reach a galaxy that is receding from you faster than light, because no matter how much you dilate your subjective time, you are still not moving through space faster than light, and the space between you and that galaxy is growing faster than light. The door is open for crossing to reachable places, but the wall that marks the boundary of unreachable space is a wall that time dilation cannot touch. So the real question becomes, what's on the reachable side of that wall? And how much of it will humanity ever actually get to? That's where we're going next. But first, I need to introduce you to something that changes the entire conversation. The thing that might be a bigger barrier than the speed of light, bigger than the cosmic event horizon, bigger than any wall we've talked about so far. The thing that might limit human travel, not in terms of distance, but in terms of time. We're talking about energy. I want to tell you about one of the most devastating equations in all of science. Not devastating in the emotional sense. Well, actually, yes, in the emotional sense too. Devastating in the sense of annihilating hope. Devastating in the sense of a single line of mathematics that has more power to define the limits of human civilization than any political boundary or resource constraint ever drawn. It's called the Tsiolkovsky rocket equation, named after Konstantin Tsiolkovsky, the Russian visionary who derived it in 1903, the same year the Wright brothers first flew. Tsiolkovsky was decades ahead of any actual rocketry, just sitting in a small Russian town writing mathematics that would eventually define the upper bound of how far and how fast any rocket-propelled craft could travel. The equation looks innocent enough. Delta V equals exhaust velocity times the natural logarithm of the ratio of initial mass to final mass. Delta V, change in velocity, is what you want. Exhaust velocity is how fast your rocket throws stuff out the back. And the ratio of initial to final mass is the critical term. It's how much of your spacecraft is fuel versus how much is the stuff you actually want to get somewhere. Here's what the equation says in plain English. Every time you want to go twice as fast, you need exponentially more fuel. About twice as much fuel. Exponentially more. And the fuel you carry to accelerate the fuel you carry to accelerate the payload. That fuel needs its own fuel. And that fuel needs its own fuel. It compounds, it cascades, it explodes upward in a way that rapidly becomes absurd. Think of it like this. Think of it like packing for a trip where every item you pack adds weight, and every pound of weight requires you to pack 1 pound of food to carry it, and every pound of food requires more food to carry that food. You want to bring a single extra pair of shoes? You end up with a refrigerator full of food. You want to bring a whole suitcase? You need a shipping container. The payload stays small. The fuel requirement explodes. Here are real numbers so you can feel this. The Saturn V rocket that took Apollo 11 to the moon weighed 2.8 million kilograms at launch. The payload that actually went to the moon? About 43,000 kilograms, roughly 1.5% of the total mass. The other 98.5% was fuel and the structure to hold the fuel. That was to go to the moon. Let's scale up. To get to Mars with a chemical rocket, you'd need a mass ratio of roughly 20-to-1 fuel to payload. To get to even the nearest star system, Alpha Centauri, at a reasonable fraction of the speed of light using chemical propulsion, you would need a mass of fuel so large compared to your payload that the numbers stop making sense. We're talking about needing a rocket the mass of Jupiter to get a school bus to Alpha Centauri. This is not engineering hyperbole. The mathematics is unambiguous. So clearly, we don't use chemical rockets for interstellar travel. Nobody serious thinks we do. The question is what we use instead. And this is where the physics of propulsion becomes one of the most fascinating and frustrating fields in all of science. Because every upgrade you make to the propulsion system makes the mission more feasible. But the feasibility curve approaches the useful only agonizingly slowly. Let's go through the candidates, because this is mind-blowing in its own right. Nuclear pulse propulsion, essentially detonating nuclear bombs behind your spacecraft to push it forward. A concept seriously studied by the US government in the 1950s under Project Orion, could, in theory, achieve exhaust velocities 10 to 100 times better than chemical rockets. This sounds revolutionary, and it is. But even with nuclear pulse propulsion, an interstellar trip to Alpha Centauri would take tens of thousands of years. You've improved by a factor of 10 or 100, but you needed to improve by a factor of millions. Antimatter propulsion is the best we can theoretically conceive of with known physics. When matter meets antimatter, it annihilates with 100% mass-to-energy conversion, which is the theoretical maximum. Compare that to nuclear fusion, about 0.7% mass-to-energy, or nuclear fission, about 0.1%, or chemical rockets, roughly 0.0000001%. Antimatter is almost incomprehensibly more efficient. A well-designed antimatter rocket could potentially reach Alpha Centauri in decades at the cost of a few grams of antimatter fuel per kilogram of payload. And here's the catch. We currently produce antimatter on Earth at facilities like CERN at a rate of roughly a few nanograms per year, at a cost of roughly $100 quadrillion per gram. To fuel a single interstellar mission, you'd need grams. At current production rates and costs, you would need the GDP of every nation on Earth for thousands of years just to fill the tank. The technological gap isn't engineering. It's physics and economics and time. But let's say, generously, optimistically, that humanity solves propulsion. Let's say we get fusion drives, or antimatter drives, or some breakthrough we haven't thought of yet. Let's say we can send ships to other stars. What then? What limits are left? Hold that thought. Because there's another wall waiting, one that has nothing to do with rockets or fuel or engineering. A wall that every rocket engineer in the world is completely powerless against. A wall that is not a question of technology, but a question of the human animal itself. I want you to think about your body for a moment. Not in a self-conscious way, in a scientific way. You are a collection of approximately 37 trillion cells, powered by glucose and oxygen, maintained at a temperature of 98.6 degrees Fahrenheit, dependent on roughly 2 liters of water per day, and designed by 4 billion years of evolution for one specific environment. The surface of Earth, within 3 miles of sea level, with a gravitational pull of exactly 9.8 meters per second squared, protected by a magnetic field and an ozone layer from the radiation that fills the rest of the solar system. You are, in the most precise technical sense, spectacularly unsuited for space travel. And this is not an engineering problem that better engineering can fully solve. This is a biological problem that goes right down to your DNA, your circulatory system, your immune system, your vestibular system, your psychology. Space does things to the human body that are extraordinary in their variety and viciousness. And the more we study long-duration spaceflight, particularly through the incredible data gathered from ISS missions and from NASA's twin study comparing astronaut Scott Kelly after his year in space with his identical twin brother Mark, who stayed on Earth, the more we realize that putting humans in space for extended periods is asking the body to do something it was never built to do. Let me give you the catalog, because this is a mind-blown moment if you've never thought about this carefully. Microgravity causes bone density loss at a rate of about 1 to 2% per month in the weight-bearing bones. Astronauts exercise 2 hours every day just to slow this down, and they still lose bone. After 6 months on the ISS, astronauts return to Earth and can't walk properly. They have to be carried out of the capsule. After a year, Scott Kelly spent months in physical rehabilitation. Now extrapolate to a multi-year trip to Mars, or a multi-decade trip to another star. The bones become fragile in ways that no amount of exercise has fully solved. Fluid redistribution. Without gravity pulling fluids toward your legs, they shift toward your head and chest. Your face puffs up. Your legs become sticks. More critically, the fluid pressure changes in your skull, pushing on your optic nerves, causing a condition called spaceflight-associated neuroocular syndrome. Many astronauts return with permanently degraded vision. We are still learning how serious this is. Cosmic radiation. The Earth's magnetic field and atmosphere shield us from a constant bombardment of high-energy particles, galactic cosmic rays from outside our solar system, and solar energetic particles from the Sun. In deep space, beyond Earth's magnetosphere, this protection is gone. High-energy particles pass through the body and through whatever shielding you build, because sufficiently energetic particles can only be stopped by very thick, dense material. And thick, dense shielding means enormous mass, and enormous mass means the rocket equation destroys you. The career radiation limit for astronauts is designed to keep cancer risk below a certain threshold. A Mars mission already pushes against this limit. An interstellar mission would deliver radiation doses that overwhelm any reasonable shielding. Then there's the psychological dimension. In 2010-2011, an international experiment called Mars 500 locked 6 people in a simulated Mars mission habitat in Moscow for 520 days, not going anywhere, just living as if on a Mars trip. Results: persistent sleep disruptions, sedentary behavior, psychological withdrawal, reduced activity as the mission wore on. And these people could get out if they wanted to. They had emergency exits. Real astronauts on a real Mars mission would have no abort option once committed. The psychological load of knowing you cannot return, that you are committed, that you are permanently beyond help, is something no simulation has fully replicated. And a trip to another star? If you send humans on an antimatter rocket at 10% the speed of light, The nearest star is a 40-year journey, 40 years in space, with a crew of, what, 10 people? 20? Living in a tin can, watching each other age, watching people they love on Earth grow old and die over a communications lag of years, dealing with a radiation environment unlike anything in human experience, with bones and eyes and immune systems in slow deterioration, with no possibility of rescue, no possibility of resupply, no familiar context, no seasons, no sky, no horizon. What if I told you that the hardest part of interstellar travel might not be the rocket equation or the radiation or the gravity, but the human mind? That the obstacle standing between humanity and the stars might be consciousness itself? The evolutionary machinery that makes us who we are, the social wiring that requires community and continuity and connection, might be structurally incompatible with the isolation and duration of interstellar travel. This is not defeatism, it's honesty. And understanding it clearly is the only path to figuring out whether and how to overcome it. But here's the thing that should really rearrange your assumptions. What if we're asking the wrong question? What if the question isn't, can humans survive a multi-decade interstellar voyage? But rather, who or what goes on the voyage at all? Because there's a possibility that the future of human expansion isn't biological humans expanding at all. It might be something we make, something descended from us, but not contained by our limitations. And depending on your definitions, that might count as humanity traveling, or it might be the moment humanity ends and something else begins. That's a question we're going to sit with, but not yet. First, I need to show you what the nearest stars actually look like, because most people have no visceral sense of just how lonely, how empty, how staggeringly isolated the region of space surrounding Earth actually is. And until you feel that emptiness in your gut, you won't understand why every obstacle we've talked about so far matters as much as it does. Let me give you a scale model of the universe. A real one, not an approximation. Because the numbers involved in space travel are so disconnected from anything in human experience that I think we have a cognitive block against really feeling them. We hear 4.2 light years to Alpha Centauri, and we nod and move on, but we don't feel it. Let me make you feel it. If the sun were the size of a grapefruit, about 10 centimeters in diameter, and we placed that grapefruit on a table in front of you, where would Earth be? Earth would be about 10 meters away, a small pebble, 10 meters from the grapefruit. That's roughly the distance across a large room. You're already getting a feel for the emptiness. In this scale model, where would the moon be? A tiny speck, about 2.5 centimeters from the Earth pebble, remarkably close. In this model, the entire Apollo program, all of human crewed spaceflight beyond low Earth orbit, was confined to a region you could cover with your hand, the International Space Station. At this scale, it orbits about a millimeter above the Earth pebble, less than the thickness of a credit card above the ground. That's where all crewed spaceflight has been for the last 50 years. 1 millimeter. Now, where is Alpha Centauri, the nearest star system in the scale model? Walk away from your grapefruit sun. Keep walking. Walk 2,700 kilometers. For my American viewers, that's roughly the distance from New York City to Las Vegas. For my European viewers, it's about London to Riyadh. That is where the nearest star is in a scale model where the sun is a grapefruit. And in between, there is essentially nothing. No planets, no asteroids, no gas clouds of significance, just vacuum, just void, just the dark. This is not an exaggeration. This is the real geometry of our cosmic neighborhood. The stars are absurdly, almost maliciously far apart. Our galaxy is 100,000 light years across and contains roughly 300 billion stars. And the average distance between stars in our neighborhood of the galaxy is about 4 to 5 light years. The galaxy is not a crowded city. It is a vast, empty wilderness with tiny campfires, separated by thousands of kilometers of frozen desert. And here's something that I think most people have never fully processed. We have been sending signals into this desert for decades, and we have heard nothing back. Since 1960, with Project Ozma, led by astronomer Frank Drake, who also developed the famous Drake equation estimating the number of civilizations in the galaxy, we have pointed radio telescopes at the sky and listened. 60+ years of listening. A few anomalies here and there. The famous WOW signal in 1977, detected by astronomer Jerry Emin, who literally wrote WOW in red pen in the margin of the printout, but nothing confirmed, nothing repeated, nothing that has risen to the level of evidence for intelligent transmission. This could mean many things. It could mean intelligent life is rare. It could mean they're not using radio. It could mean they're not interested in talking. It could mean they were there, but are now gone. It could mean the distances involved are simply so vast that even civilizations broadcasting for millions of years are too diluted by distance for us to detect. The Milky Way is a big place. But here's what it definitely means. The desert between the stars is real, and it is deep, and it offers no reassurance that crossing it leads somewhere interesting on the other side. Now here's the mind-blown moment I promised you. What if I told you that of all the stars in the Milky Way, all 300 billion of them, we have only done meaningful astronomical analysis on a tiny fraction? We have detailed information on the spectra and planetary systems of perhaps a few thousand stars from direct exoplanet research. The Kepler Space Telescope, launched in 2009, revolutionized this by staring at a small patch of sky and detecting planets by the dimming of their host stars as planets transited in front of them. Kepler found over 2,600 confirmed planets and suggested that nearly every star has planets. Every star, not most stars. Nearly every star in the galaxy appears to host a planetary system. This is astonishing. It means the desert is full of oases, planets everywhere. Rocky planets, gas giants, ice worlds, the galaxy is positively dripping with planets. And subsequent work by the TESS mission and ground-based observatories has confirmed this picture. We now estimate there are more planets in the Milky Way than there are stars. Roughly 100 billion or more Earth-sized rocky planets, a significant fraction of which orbit in the habitable zones of their host stars. And the nearest of these potentially habitable planets? Proxima Centauri b, orbiting Proxima Centauri, the closest individual star to Earth at 4.2 light-years. Discovered in 2016, its roughly Earth mass in the habitable zone of its host star. It might have liquid water. It just might, be inhabited or habitable. And it would take the fastest spacecraft we've ever launched, the Voyager probes, moving at roughly 17 kilometers per second, about 75,000 years to get there. Let that land. 75,000 years to the nearest possibly interesting world. Using our fastest spacecraft, 75,000 years. That's 5 times longer than recorded human history. That's longer than Homo sapiens have existed as a distinct species with modern cognitive abilities. This is why the rocket equation matters. This is why propulsion matters. Because the nearest target worth visiting is 75,000 years away by our current standards, and everything beyond it is orders of magnitude farther. But here's the cliffhanger. I've been talking as if the nearest stars are the limit of human ambition. They're not. Not even close. The real walls, the ones that genuinely define the maximum extent of possible human expansion in this universe, are cosmological, not just local. And to understand them, we need to zoom out from the Milky Way, way out, past the local group, past the Virgo supercluster, out to the scale where the universe itself shows you its architecture. And at that scale, something extraordinary becomes visible. Something that no one in history knew about until a few decades ago. Something that makes the space between stars look cozy by comparison. Let me zoom out. Forget individual stars. Forget even the Milky Way for a moment. I want to talk about the large-scale structure of the universe, because understanding what the universe actually looks like at its biggest scales is essential to understanding the limits of travel within it, and because it's genuinely one of the most beautiful things science has ever discovered. The universe, at the largest scales, is not uniformly filled with galaxies. Galaxies clump together into groups. Groups cluster into clusters. Clusters arrange into superclusters. And superclusters organize into something extraordinary, a cosmic web. A vast, three-dimensional lacework of filaments and sheets and walls made of dark matter and galaxies, surrounding enormous voids that contain almost nothing, no galaxies, no stars, just empty space hundreds of millions of light years across. This was not obvious. For much of the 20th century, cosmologists assumed the universe was roughly uniform at large scales. Galaxies spread more or less evenly, with some clumping, but nothing dramatic. Then in the 1980s, surveys of galaxy positions began to reveal the shocking truth. Margaret Geller and John Hoekra at the Harvard-Smithsonian Center for Astrophysics, mapping the positions of thousands of galaxies in 1986, discovered what they called the Great Wall, a sheet of galaxies roughly 500 million light-years long and 300 million light-years wide. This was the first discovery of what we now recognize as the cosmic web's filamentary structure. Since then, we've mapped the universe at ever larger scales, and the picture has only become more dramatic. The Sloan Great Wall, discovered in 2003, is nearly 1 billion light-years long. The Hercules Corona Borealis Great Wall, identified in 2013, is roughly 10 billion light-years long, about 1/14 the diameter of the observable universe. It is the largest known structure in the universe. Think of it like this. Think of it like the universe is a sponge. The foam of the sponge is where the galaxies and clusters are. The holes in the sponge are the cosmic voids. From any given galaxy, like ours, you are embedded in the foam, connected to other galaxies, pulling on them gravitationally, being pulled. But around you, at various distances, are these enormous holes, these voids, where you would find almost nothing for hundreds of millions of light years in every direction. Our own galaxy sits in a relatively modest structure called the local group, about 50-some galaxies including the Milky Way, Andromeda, and a scattering of smaller dwarfs, all loosely gravitationally bound, all within about 10 million light-years of each other. This is our neighborhood. Beyond that, we're part of the Virgo supercluster, which contains about 100 galaxy groups and clusters spread over 110 million light-years. And that, in turn, is part of an even larger supercluster called Laniakea, discovered and named by astronomer Brent Tully in 2014, which contains 100,000 galaxies and spans 520 million light-years. Laniakea. In Hawaiian, it means immeasurable heaven. Tully chose the name because Hawaiian navigators traditionally used the stars to navigate the Neap Pacific, finding their way across an ocean that must have seemed immeasurable, and he thought there was something fitting about using a Hawaiian word for a supercluster that represents our cosmic home. And here is the crucial thing about Laniakea and everything within it. It is gravitationally bound. Not tightly, not uniformly, but the galaxies and clusters within it are, to varying degrees, falling toward each other, attracted gravitationally, part of a connected large-scale dynamic. They are, in the broadest sense, reachable from each other. The expansion of the universe is pulling them apart, but the gravitational attraction is real and significant. Beyond Laniakea, however, the distances become so vast and the expansion so dominant that gravitational attraction becomes negligible at those scales. The neighboring superclusters, Perseus Pisces, Shapley, the great cosmic neighborhood beyond our local web, are already receding from us. Some are already within or approaching that event horizon we discussed. They are, for practical purposes, beginning to slip away. This is the architecture of our cosmic allowance. Our local group is gravitationally bound. Those galaxies won't run away. They are, in principle, there to explore forever. But they're mostly dwarf galaxies. The only really large one heading toward us is Andromeda, which is approaching on a collision course and will merge with the Milky Way in about 4.5 billion years, in an event that will be spectacular and violent and transformative for both galaxies. Beyond the local group, things get complicated. The Virgo cluster, the nearest rich cluster of galaxies, about 50 to 60 million light-years away, is technically slightly pulling our local group toward it, but the expansion is winning. It's neither strongly reachable nor strongly out of reach. It's in a kind of limbo. And beyond that, beyond Laniakea, the picture becomes clearer and darker. Those structures are receding. Those galaxies are already on their way over the horizon. Our grandchildren's grandchildren's grandchildren, if they develop interstellar travel, might technically be able to launch missions towards some of them before they cross the horizon. But realistically, practically, the universe accessible to life that originates in the Milky Way is probably the local group, plus a small surrounding volume. Perhaps a few dozen galaxies, most of them small, none of them very interesting compared to the Milky Way or Andromeda themselves. 3 million galaxies are technically within the cosmic event horizon, as we've defined it, reachable if you launch today and accelerated indefinitely. But the vast majority of those 3 million are tens of billions of light years away, and reaching them would require civilization-scale engineering projects sustained over tens of billions of years, which creates its own set of physical constraints we haven't even talked about yet. For practical purposes, the universe that a civilization based in the Milky Way could ever exploit, explore, and expand into? It's the local group, maybe a bit beyond, that's it. In a universe of 2 trillion galaxies, we have access to maybe 50, maybe a few hundred if we're being extremely generous about timescales and technology. Does that make you feel small? It should. And it should also make you feel something else, something I want to spend the next section unpacking. Because this architecture has an implication that I think is one of the most important and underappreciated ideas in all of cosmology. An implication about the relationship between cosmological time and the possibility of civilization. Here's the teaser. The universe is not equally hospitable to civilization at all times. Right now, in this moment of cosmic history, we happen to be living in a kind of sweet spot. And that sweet spot is temporary. And understanding why it's temporary tells us something profound about why now matters more than anything that comes after. I want to ask you a question that sounds philosophical, but is actually scientific. Is this a good time to be alive in the universe? Not in terms of human civilization. Ignore wars and politics and pandemics. I mean cosmologically. Is Earth, in the year 2024, a fortunate or unfortunate address in the space and time of the universe? The answer is extraordinarily fortunate. And the reasons why are going to reframe everything we've been discussing. Let's think about stars. Stars are the furnaces that make everything interesting in the universe. Stars produce heat and light. Stars synthesize heavy elements through nuclear fusion. Carbon, oxygen, nitrogen, iron. Everything in your body was made in a star. Stars power the chemistry of life. Without stars, the universe would be just hydrogen, helium, and darkness. The first stars formed about 100 million years after the Big Bang. They were enormous and lived fast and died explosively, seeding the universe with the first heavy elements. Over billions of years, subsequent generations of stars have been building up the chemical complexity of the universe, creating the iron and carbon and oxygen and calcium and phosphorus that biology requires. But here's what's fascinating. Star formation in the universe peaked about 10 billion years ago. Since then, it has been declining. The universe is, gradually, running out of the gas clouds that collapse to form new stars. The rate of star birth today is about 10 times lower than it was at the peak. And this decline will continue. In roughly 1 trillion years, star formation in the universe will essentially cease. The last red dwarf stars will keep burning for perhaps 100 trillion years. 10,000 times longer than the current age of the universe, and then they too will go out. We live 13.8 billion years after the Big Bang, when the universe still has abundant stars, when the chemistry of life has had time to build up complexity, but the stars haven't yet exhausted their fuel. We are, in a very real sense, living in the era of stars, the brief golden window in cosmic history when the universe is lit up, warm, chemically complex, and hospitable. Before us, not enough heavy elements, too much radiation from the early universe's extreme temperatures. After us, eventually, a cooling, dimming universe running down to darkness. We are in the middle of a cosmic sweet spot, and we don't notice it because 13.8 billion years feels like a long time to us, not a brief window. But set it against the trillion-year lifespan of the universe, and it is, cosmologically, a brief window. Now here's where it connects to everything we've been saying about travel. The cosmic event horizon, at wall at 16 billion light-years, is not static. As the universe accelerates, it shrinks. The number of galaxies accessible to us is decreasing, and the rate at which it decreases is not slow by cosmological standards. We are currently in the period where a technologically capable civilization could launch probes that would eventually reach distant galaxy clusters. In roughly a few billion years, that window closes permanently. No matter how advanced the technology, no matter how powerful the rockets, there will come a point where no spacecraft launched from the local group can ever reach the next galaxy cluster over, because the expansion will have made that cluster permanently, irrevocably unreachable. And here's the part that blew my mind when I first thought about it carefully. That means that whether or not humanity, or whatever descendants of humanity exist, chooses to expand into the cosmos over the next few billion years is literally a once-in-the-universe decision. If they don't expand now, when expansion is still possible, it will become impossible. No later civilization in the local group will ever have the option again. The universe allows cosmic expansion for a limited time only, and that limited time is, cosmologically speaking, soon. We are not early in the possible window. We are approaching the middle of it. This is what cosmologist Lawrence Krauss and others have noted in a paper by Krauss and Robert Scherer called The Return of a Static Universe and the End of Cosmology, published in 2007. They showed that in the far future, as the universe's accelerating expansion removes all distant galaxies from view, future intelligent beings will look out at a universe that appears to be just their local group floating in an otherwise empty cosmos. They will have no evidence of the Big Bang. They will have no evidence of cosmic expansion. The cosmic microwave background radiation that currently gives us our best evidence for how the universe began will have been redshifted to invisibility. They will be, in the most complete epistemological sense, blind to the history and structure of the universe. We are the civilization that happens to exist at the moment when the full grandeur of the cosmos is still visible, when the evidence is still accessible, when the universe is still showing us its complete picture. And here's the personal punch. You, reading this, looking at the night sky, watching this video, you are one of the last beings in the entire history of the universe to see the universe in its full scope. In cosmic timescales, the window is closing. What we can see from Earth today with our telescopes is a view that will never be replicated. Future beings, if they exist, will be trapped in ignorance of what we can see. That is not a reason for despair. It is a reason for reverence. We are custodians of a view. We are the eyes the universe turned on itself at exactly the moment when there was the most to see. But the story I'm building has another layer. Because everything I've told you so far has been about external limits, the limits imposed by the universe's structure, its expansion, its scale, and those are real and absolute. But there's another class of limits, internal limits, limits inside physics itself, that are in some ways even more sobering. Let's talk about energy, not rocket fuel, not stellar fusion. Let's talk about the maximum possible energy available to a civilization, anywhere in the universe, ever. Because there is such a maximum. And calculating it forces us to confront the full shape of what's possible. In 1964, a Soviet astrophysicist named Nikolai Kardashev proposed a scale for measuring the technological advancement of civilizations, not in terms of their culture or knowledge, but purely in terms of their energy consumption. The reasoning was elegant. The more advanced a civilization, the more energy it can harness and use. Energy is the universal currency of technology. A Type 1 civilization, on Kardashev's scale, harnesses all the energy available on its home planet. All sunlight falling on the surface, all geothermal energy, all wind and ocean. Earth today uses roughly 20 terawatts of energy. The total solar energy reaching Earth's surface is about 170,000 terawatts. We are currently at about 0.7 on the Kardashev scale. Not even Type 1 yet. A Type 2 civilization harnesses all the energy output of its host star. For our Sun, that's about 3.8 times 10 watts, roughly 17 billion times the energy Earth's surface receives. The theoretical structure for doing this is a Dyson sphere, first described by physicist Freeman Dyson in 1960. Essentially, shell or swarm of structures surrounding a star, capturing its entire energy output. This is physically possible. It is extraordinary engineering, but it doesn't violate any known laws of physics. A Type 3 civilization harnesses all the energy of its host galaxy. That's 10 stars, each potentially surrounded by a Dyson sphere, channeling energy to a galaxy-spanning civilization. The numbers are beyond comprehension, roughly 10 watts. And here's what's important about this framework for our discussion. Each step up the Kardashev scale dramatically increases what's possible in terms of expansion. A Type 2 civilization could launch relativistic starships without being constrained. By fuel scarcity, you have a star's entire output at your disposal. A Type 3 civilization could launch von Neumann probes, self-replicating spacecraft that travel to new star systems, harvest local resources, build copies of themselves, and fan out across the galaxy in a wave that could cover the entire Milky Way in a few million years. A few million years sounds long, but in a 10-billion-year-old galaxy, it's nothing. If any civilization anywhere in the Milky Way had achieved Type 3 status even 100 million years ago, we would expect the entire galaxy to already be saturated with their probes and structures. We would expect to see Dyson spheres everywhere we look. We would expect the galaxy to look clearly artificial in detectable ways. We see none of this, which either means no civilization has reached Type 3 in the Milky Way, at least not in our vicinity, or there's something about the path to Type 3 that is extraordinarily difficult or universally fatal. This is one dimension of the Fermi paradox, and it's one of the deepest unsolved problems in science. We'll come back to this. But right now, I want to focus on the energy limits, because they define a hard ceiling on what is possible. Think of it like this. Think of it like the cosmic energy budget as a bank account. Stars are the interest payments, steady energy flowing out from nuclear fusion. But the principle, the total mass energy of the universe, is finite. And here's a sobering truth from thermodynamics. Not all of it can be used. In fact, most of it cannot be used. The second law of thermodynamics says that in any energy conversion, some energy is always lost as heat that flows from hot to cold and eventually equalizes. The universe started in an extraordinarily low entropy state, hot in some places, cold in others, with enormous gradients that allow work to be done. It is progressing toward a high entropy state, everything at the same temperature, no gradients, no work possible, no information processing possible, no life possible. This is heat death, and it is the ultimate cosmological limit. On the timescale of the universe's life, we are early in this process. The gradients are still enormous. Stars are still burning. The cosmic bank account has most of its principal intact, but it is being spent. Every star that shines, every Dyson sphere that harvests solar energy and converts it to work, every spacecraft that flies, every thought that is thought, these all generate entropy. They all move the universe incrementally toward heat death. This is not something technology can overcome. It is not something intelligence can outsmart. The second law is perhaps the most ironclad of all physical laws. It has no known exceptions. It applies everywhere, at every scale, at every moment. Heat death is not a threat that future civilizations can engineer around. It is the final, unbreakable wall. But here's what's interesting, and here's the mind-blown moment I want to land right now. The second law means that the act of exploration and expansion is not free, even in principle. Every civilization that expands consumes more energy and produces more entropy. The universe's capacity to support complexity, life, intelligence, civilization is finite. Not just practically finite because of resource constraints, but fundamentally finite because of thermodynamics. There is a maximum amount of computation, a maximum amount of thought, a maximum amount of experience that can ever occur in the entire future of the universe. Physicist Freeman Dyson explored this in a 1979 paper called Time Without End, asking whether intelligence could survive indefinitely in a universe heading toward heat death. His answer was carefully optimistic. If the universe continued to expand and cool, but not completely freeze, intelligence could theoretically survive forever by slowing down its processes, thinking more and more slowly to take advantage of ever smaller temperature gradients, like a hibernating creature in a cooling world. But subsequent work by Lawrence Krauss and Glenn Starkman showed that in an accelerating universe, which ours is, even this strategy fails. The accelerating expansion actually imposes a fundamental limit on how much information can ever be processed, ever, by any intelligence anywhere. The number they calculated, about 10 bits of information, can be processed in the entire future of our observable universe. That sounds large, and it is, but it is finite. It means there is a maximum number of thoughts that can ever be thought, a maximum number of experiences that can ever be had, a maximum amount of art, science, love, discovery that can ever occur. And here's what makes this land personally, viscerally. Every thought you think is a fraction of that total. Every moment of beauty you experience, every problem you solve, every connection you make, these are irreplaceable expenditures from a finite cosmic budget. The universe has a limited capacity for experience, and you are using it right now. That's either the most depressing thing I've ever said, or the most profound. Possibly both. Subscribe, comment. I'm not kidding. This is the kind of stuff I want to know you're watching. Drop a comment telling me the most mind-blowing thing you've heard in this video so far. I read them. This community keeps me making these videos. And hold tight, because we're about to get personal. We've been talking about limits that are billions of light years away. Now I want to bring it home. I want to talk about what these limits mean for you, for human beings alive today, and for the species over the next 1,000 years. Let me bring this all the way back to Earth. Literally, we've talked about the cosmic event horizon. We've talked about the limitations of the rocket equation. We've talked about the biological fragility of the human body in space. We've talked about energy budgets and thermodynamics. All of these are real. All of them matter. But none of them stop us from going to the moon next year, or Mars in the next decade, or the asteroid belt in the next century. The walls that are cosmologically absolute don't interact with near-term exploration. So what does the actual roadmap of human expansion look like? Not the science fiction version. The physics-constrained, engineering-realistic, actually achievable given what we know version? Let's build it honestly. The moon first. NASA's Artemis program, currently aiming to return humans to the lunar surface in 2025 or 2026, represents the first step in what must be a sustained lunar presence. The moon is 3 days away at current velocities. It has water ice at its poles, confirmed by multiple missions including India's Chandrayaan-1 and NASA's LCROSS impact mission in 2009. That water is critical, not just for drinking, but for hydrogen fuel and oxygen, which means the moon could serve as a refueling stop and staging point for deeper space exploration. The moon's low gravity, 1/6 of Earth's, means launching from the lunar surface costs enormously less energy than launching from Earth. The moon is achievable. It's hard, it's expensive, but it's within the capability of existing technology. It's not a cosmic limit question. It's a political and economic question. Mars is harder. The transit time with current propulsion is 6 to 9 months, depending on orbital alignments that only allow efficient launch windows every 26 months. Missions are being planned. SpaceX's Starship program is explicitly aimed at Mars. And Elon Musk has stated publicly he wants to establish a city of 1 million people on Mars within the next few decades. That timeline is almost certainly optimistic to the point of fantasy, but the goal itself is not physically impossible. The challenges for Mars are exactly what we discussed earlier: radiation, bone density, psychological isolation, and the fact that unlike the moon, Mars is far enough away that emergency return is not possible. Once committed to a Mars transit, you're committed. A psychological and medical screening for Mars astronauts will need to be extraordinarily rigorous. But here's where it gets really interesting from a physical limits perspective. Establish Mars, and what do you have? You have a backup civilization. This is the point that people like Musk and cosmologist Stephen Hawking have made forcefully. Humanity is currently a one-planet species, and that makes us extraordinarily vulnerable. A large asteroid impact, a supervolcanic eruption, a pandemic, a nuclear war, any of these could end human civilization entirely if we're confined to Earth. A 2-planet civilization is vastly more robust. A 10-planet civilization is essentially indestructible. From the asteroid belt to Jupiter's moons, the solar system offers extraordinary resources. The asteroid belt alone contains enough metal and mineral wealth that, if distributed equally to all humans alive today, each person would receive trillions of dollars worth of material. Asteroid mining is not science fiction. It is currently being studied seriously by multiple governments and companies. The asteroids are easier to reach than Mars in terms of delta V, the energy required, because they have no significant gravity wells. Jupiter's moon Europa has a liquid water ocean beneath its ice shell. We know this from magnetic field measurements by NASA's Galileo spacecraft in the 1990s, and it has been confirmed by multiple subsequent observations. That ocean contains more liquid water than all of Earth's oceans combined. It has existed for billions of years. Europa is one of the most compelling targets in the solar system for the search for life. Saturn's moon Titan has lakes and rivers and a thick atmosphere, not water, but liquid methane, and a chemistry so rich and bizarre that it might be a completely alien form of life's starting point. Carl Sagan and Bishun Kher speculated in the 1980s that Titan's orange haze contained organic chemistry at a scale that made it a prebiotic chemistry laboratory. Everything we've learned since has deepened that assessment. The solar system alone, just our star and its retinue of 8 planets, hundreds of moons, millions of asteroids, billions of comets, is so rich in resources, so full of unexplored environments, so packed with scientific wonders that a civilization could spend millions of years exploring it without reaching its limits. And the solar system is, compared to interstellar distances, impossibly close to home. The farthest reaches of the Oort cloud, the cloud of comets that surrounds the solar system at distances of up to a light year or 2, is still gravitationally bound to the sun. Everything within the Oort cloud is, in some sense, ours. It is within reach. It is the local neighborhood. Think of it like this. Think of it like the solar system is a continent. We've explored one small island, Earth. We've briefly visited one beach on a neighboring island, the moon. We've sent robot boats to several other shores. But the continent itself, in all its richness, remains essentially unvisited. A civilization that chose to explore and inhabit the full solar system, from Mercury to the outer Oort cloud, would be a civilization busy for geological timescales. There is enough there. So here's the question that I want to pose, and it's one that cosmologists and philosophers actually argue about. Should we care about the interstellar barriers? Should the walls 100,000 light years away affect how we feel about a civilization that has an entire solar system to explore? I think the answer is a complicated yes. And here's why. The walls matter not because they determine what we do in the next 100 years, but because they define the meaning of what we do. They set the context. They tell us what kind of universe we live in. And a universe that has a wall, that limits what is possible, that puts a ceiling on the total scope of experience and complexity. That universe requires us to make different choices, to have different values, to assign different worth to different acts than a universe that is infinite and open. Knowing the walls there changes everything. Not the engineering, the philosophy. And speaking of philosophy, we are coming up on the moment in this video where I want to talk directly to you. Not to the abstract you of an audience, but to the actual person watching this. Because there's a personal dimension to all of this that I haven't addressed yet. I want to get personal with you. Everything we've talked about in this video, the cosmic event horizon, the rocket equation, the biological limits of the human body, the thermodynamic ceiling of the universe, all of it can feel very abstract, very out there, very much like information that exists in a special compartment called space stuff and doesn't connect to your actual life. But I think it connects to your life more directly than almost anything else you'll ever learn. And I want to take a few minutes to explain why. First, let's talk about the overview effect. In 1987, writer Frank White coined this term for a cognitive shift reported by virtually every astronaut who has seen Earth from space. The first time you see the planet from outside, this blue marble hanging in absolute black, no borders, no divisions, just ocean and cloud and land, and the thin filament of atmosphere. Something changes in you that apparently can't be unchanged. Astronauts describe it as a profound feeling of interconnection, a visceral understanding that the boundaries we fight over are arbitrary, that the fragility of our world is not metaphorical but literal, that we are all inhabitants of the same very small, very vulnerable vessel. Edgar Mitchell, Apollo 14 astronaut and the sixth person to walk on the moon, described it as an explosion of awareness. He said, "The Earth is hanging in darkness, this beautiful blue-white jewel with a thin, fragile halo of atmosphere. And I said to myself, that little thing is so fragile out there." Mitchell reportedly had an epiphany on the return journey from the moon, a sudden, overwhelming sense of unity and connectedness that changed the entire direction of his life. You might never go to space. The probability for almost any given person alive today is negligible. But you can think your way to something like the overview effect by really sitting with what this video has been showing you. Consider, we live on a rock orbiting a star that is one of 300 billion stars in the Milky Way. Our galaxy is one of 2 trillion galaxies in the observable universe. All of human history, every war, every empire, every invention, every love story, every moment of suffering or joy has occurred on a pale blue dot. As Carl Sagan famously described it, that would be invisible to any observer even from the orbit of Neptune. And yet, here's the thing that should hit you with force. This pale blue dot is almost certainly one of the most interesting places in the observable universe right now. Not because of its size, not because of its position, but because of what's on it. Life. Complex, conscious, curious life. Life that has looked up at the stars and asked questions about them. Life that has built telescopes and mathematics and philosophy. Life that has, in the last century, figured out the large-scale structure of the universe from this one small vantage point. The philosopher Nick Bostrom has argued that intelligence might be extraordinarily rare in the universe. The biologist Ernst Mayr argued that the evolution of human-level intelligence was so improbable that it might have happened exactly once in the Milky Way's history. We don't know. But the possibility that conscious awareness, capable of contemplating the cosmos, might be rare, maybe very rare, gives this blue dot an importance that its size completely belies. You are not small because your planet is small. You are immense because what happens in your consciousness, the ability to understand, to wonder, to know, might be one of the rarest and most extraordinary phenomena in the observable universe. And here's where it connects back to the walls. The walls we've been discussing, the cosmic event horizon, the limits of travel, the thermodynamic ceiling. These walls mean that the window for exploration and expansion is finite, not infinite, not forever. There is a limit on the total amount of experience and understanding that can exist in the universe. And every moment of genuine understanding, every act of real curiosity, every instance of actually grappling with the nature of reality rather than looking away, these are irreplaceable contributions to that finite total. What I'm saying is, your curiosity matters. Not in a motivational poster sense, in a cosmological sense. In a universe with a finite capacity for experience, the experiences you have, the thoughts you think, the understanding you achieve, these are not trivial. They are part of the universe understanding itself. And that is the only enterprise the universe has. Carl Sagan said it. We are a way for the cosmos to know itself. The universe is not just a place where things happen. It is a process that, in the case of life and intelligence, has developed the ability to look inward and outward simultaneously and ask, what is this? Where does it come from? Where does it go? That process is happening in you right now, watching this video. And the walls that define the limits of where humanity can physically travel, they don't constrain that. No wall in the universe can stop a human mind from contemplating the universe. The physical frontier has limits. The interior frontier does not. But here's what I haven't told you yet. Here's the thing that, for me, ties the whole story together. We've been talking about limits as if they're purely constraining. Walls that stop us, horizons that shrink. But there's a way of looking at limits that is exactly the opposite. A way of understanding that the universe's finiteness is not the universe's cruelty, but the universe's gift. And to get there, I need to take you through two more big ideas. The first is about what happens to the universe after us, not after humans, but after stars, after matter, after everything. The full story of the cosmic long term. And the second is about the question of whether these limits even apply if we're willing to change what we are. Let's go to the death of the universe. Because understanding the end makes the middle, which is where we are, make sense in a way nothing else can. Let me tell you the future of the universe. All of it, from now to the end. We are currently 13.8 billion years after the Big Bang. The universe is in what cosmologists sometimes call the stelliferous era, the age of stars. This will continue for roughly another 100 trillion years. 100 trillion years of stellar fire, of nuclear reactions in the hearts of suns, of planets and moons, and the possibility of life. In the grand timeline of the universe, we are extraordinarily early. 100 trillion years dwarfs the current age of the universe by a factor of 7,000, but nothing lasts. After the stelliferous era, the last red dwarf stars will exhaust their fuel and cool to black dwarfs, cold, dark remnants no longer shining. The universe enters the degenerate era, when the only stellar objects are these cold, dark dwarfs, neutron stars, and black holes. The universe is dark. There is no more starlight. Any life that survives into this era, and theoretical physicists like Freeman Dyson have explored whether and how life might adapt, would need to find energy from other sources. Gravitational energy, radioactive decay, the Hawking radiation from black holes. from about 10 years to 10 years after the Big Bang, the degenerate era. During this time, a process called proton decay, predicted by most grand unified theories of particle physics, though not yet confirmed experimentally, may disintegrate all normal matter. Your body, if it somehow survived until this point, would dissolve. The atoms themselves are not permanent. Given enough time, even atoms fall apart. After that, the black hole era. From about 10 to 10 years after the Big Bang, only objects remaining are black holes of various sizes, slowly evaporating via Hawking radiation. Stephen Hawking theorized in 1974, one of the most important theoretical results in modern physics, that black holes are not perfectly black. They slowly radiate energy due to quantum effects near the event horizon, losing mass over enormous timescales until they finally evaporate entirely. A black hole the mass of the Sun would take about 10 years to evaporate. A supermassive black hole would take about 10 years. And then, the dark era. After 10 years, all black holes have evaporated. All matter has decayed. The universe contains only photons, electrons, positrons, and neutrinos, all of the same temperature, all at unimaginably low temperatures near absolute zero, all at enormous distances from each other due to the continuing expansion. No gradients, no heat flows, no work possible, no information processing possible, no thought possible. Heat death. This is the end. Not an explosion, not a collapse, not a dramatic finale. Just equilibrium. The universe finally, completely, irreversibly at rest. The last entropy gradient erased. The last computation completed. Think of it like this. Think of it like the universe is a battery. At the Big Bang, it was fully charged. Enormous temperature differentials, enormous gradients, maximum capacity for work. It has been discharging ever since. Life, stars, galaxies. All of these are processes happening because of that discharge, like lights being powered by the battery as it drains. Eventually, the battery reaches zero. The lights go out. The house is dark and silent. And somewhere in those 100 trillion years of the Stelliferous era, somewhere in that vast middle of the battery's discharge, we are here. Right now, the lights are on. The universe is warm and bright and full of complexity. We are, in the most literal physical sense, the beneficiaries of the universe's charge. Every day you exist is a day the universe is powering you, not metaphorically. The atoms in your food were processed by stars. The air you breathe was cycled through billions of years of geological and biological processes. The photons hitting your eyes were fused in the core of a star 8 minutes ago. You are a temporary whirlpool of order in a river flowing toward disorder. And the fact that you get to be a whirlpool at all, rather than the ambient temperature of the distant future, is a cosmic lottery win of improbable proportions. Now here's the question that this timeline forces us to answer. Given that the stars go out, given that matter eventually dissolves, given that even the black holes finally evaporate, given that the end state is unchangeable, does anything we do matter? Not in a nihilistic sense. I want to engage with this seriously. Does the finite nature of everything change its value? I believe, and I think the physics actually supports this, that finiteness is not the enemy of meaning. It is the precondition for meaning. A universe that lasted forever, with infinite time and infinite possibility, would actually be a universe where nothing was precious, because nothing was irreplaceable. The finiteness of the universe's capacity for experience is what makes each experience irreplaceable. The people who live in the Stelliferous era, that 100 trillion year window of warmth and light, are lucky. We are among the luckiest of the lucky, because we live early in that era, when the universe's complexity is still building rather than declining, when there is still so much to discover. And the limits on travel? The cosmic event horizon, the rocket equation, the thermodynamic ceiling? These are the universe's way of saying, this is your home, not a prison. A home, a bounded, precious, finite home, with a sky full of light and room to explore for millions of years, and a hard edge that defines the preciousness by marking its end. But I still haven't answered the deepest question. The question of whether those limits apply if we change what we are. If we are willing to extend ourselves into non-biological forms, into AI, into uploaded minds, into von Neumann probes that carry human values and culture and identity across the galaxy. Do the limits change? Do the walls fall? This is the final frontier we need to explore. And it's the most philosophically loaded of all. If you mean biological Homo sapiens, unchanged, as we are today, the answer is almost certainly the solar system, and possibly with extraordinary effort, a handful of nearby star systems over the next 1,000 years. The walls are too high and our bodies too fragile for more than that in any realistic near-term scenario. But if you mean something broader, the descendants of humanity, beings that originated from us, that carry what we consider our most essential qualities of curiosity and self-awareness and moral concern, then the walls look very different. Let me walk you through the possibilities, not as science fiction, but as physics and philosophy. First possibility, biological augmentation. If we can extend the human lifespan significantly through genetic engineering, telomere therapy, organ replacement, nanotechnology, then the subjective duration problem of interstellar travel becomes tractable. A human who lives for thousands of years can make a 50-year interstellar voyage and arrive with most of their life ahead of them. They can establish a presence in a new star system and have time to build something meaningful before death. Life extension doesn't change the physics of travel, but it changes the human relationship to time, which changes everything about feasibility. The science here is real, if preliminary. Researchers like Aubrey de Grey, with his SENS Research Foundation, argue that aging is a form of cellular damage that is in principle repairable. David Sinclair at Harvard has published research on longevity genes and compounds that extend healthy lifespan in animal models. We are at the very beginning of understanding the biology of aging, but the trajectory of the science suggests that significant life extension, decades, perhaps eventually centuries, is not ruled out by any physical law. Second possibility, mind uploading. If consciousness is a pattern of information processing, an assumption that many philosophers and neuroscientists take seriously, though not without controversy, then in principle, the pattern can be copied and run on different hardware. A mind uploaded to a computer system is not subject to the biological limitations of space travel. No bone density loss, no radiation damage, no need for air or water or food. Such a mind could be transmitted as information, as radio waves, essentially, at the speed of light, making the interstellar communication problem trivially easy. Could such a transmitted mind be meaningfully you? This is one of the deepest questions in philosophy of mind, and there's no consensus. But if the answer is yes, then the walls of travel essentially fall for intelligence, if not for bodies. You could copy your mind as information, beam it toward Alpha Centauri at the speed of light, have it received and instantiated on hardware built by a waiting robot infrastructure, and you would be there in 4.2 years. The walls of the cosmic event horizon would still apply. You can't beam yourself faster than light, and the event horizon cuts off beyond roughly 16 billion light years. But within the accessible universe, the barriers become information barriers rather than physical travel barriers. Third possibility, von Neumann probes. Self-replicating robotic spacecraft named after the mathematician John von Neumann, who first formally described self-reproducing automata in the 1940s, could travel to a distant star system, use local resources to build copies of themselves, and send those copies onward. Such a wave of probes could cross the galaxy in a few million years, with each probe carrying the full archive of human knowledge and culture, and in a mind-uploading scenario, instantiated human minds. The galaxy would not need to be physically visited by biological humans. It would be visited by our intellectual descendants, our digital emissaries, versions of us that carry our values and curiosity while being free of our biological constraints. This scenario, sometimes called the seeding or transcendence approach to cosmic expansion, is the most consistent with the physics. It doesn't violate the speed of light. It doesn't require exotic propulsion. It just requires time, self-replication, and the willingness to extend our definition of us beyond biological boundaries. But here's the philosophical wall that this raises, and it's the one I find most interesting and most unresolved. If a von Neumann probe reaches a star system 1,000 light-years away and instantiates a digital mind that considers itself human and carries human values, is that humanity's expansion? Or is it the creation of a new being that merely traces its origins to humanity, the way humans trace their origins to fish? There is no clean answer. It depends on what you think humanity is. If humanity is a biological species defined by its DNA, then von Neumann probes aren't humanity traveling. If humanity is a lineage of values and curiosity and self-awareness, then they are. And if humanity is a community of lived experience and shared present moment existence, then they are not. Because a being living on a planet 1,000 light-years from Earth, separated by thousands of years of divergent experience, is not part of any community with us. The walls of physics might ultimately be less limiting than the walls of identity. You can, in principle, send something to the far reaches of the reachable universe. Whether what arrives is still you, whether it is still humanity, is a question that the universe leaves entirely to us to answer. And there's one more possibility I haven't mentioned yet, one that some physicists take seriously, though it requires physics beyond what we currently understand, and one that would, if real, completely dissolve every wall we've discussed. Warp drives. Not science fiction warp drives, the real thing, or as real as something purely theoretical can be. This is not prohibited by known physics. Einstein's equations allow it as a mathematical solution. What's not clear is whether it's physically achievable, and the problems are severe. First, to create an Alcubierre drive, you need exotic matter, matter with negative energy density. Normal matter has positive energy density. Negative energy density is not something we've ever created in macroscopic amounts, though tiny quantum effects do allow negative energy in certain configurations. To warp space on the scale of a spacecraft, you'd need vast quantities of negative energy. Early estimates suggested the mass energy equivalent of the planet Jupiter in negative form. The problem is that reducing the energy requirement doesn't solve the exotic matter problem. We still don't know how to produce negative energy in controllable macroscopic quantities, and there are fundamental reasons to doubt it's achievable. But the key word there is doubt, not proof of impossibility. Wormholes are in a similar category. Einstein and Nathan Rosen described what we now call wormholes in 1935, mathematical solutions to general relativity that describe tunnels connecting two separate points in spacetime. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a deep connection between quantum entanglement and wormholes. The A=EPR conjecture, suggesting that quantum entanglement might literally be tiny wormholes connecting entangled particles. This is cutting edge and speculative, but it connects two of the deepest areas of modern physics in a way that suggests we may not fully understand the geometry of spacetime yet. I want to end with something that surprised me when I discovered it. Not a new piece of physics, not a new discovery. A new way of feeling about everything we've covered. We started this video with a wall, an invisible boundary at roughly 16 billion light-years, beyond which no signal, no ship, no influence of any kind can ever travel from Earth. A permanent, absolute, cosmologically real limit on the scope of everything that originates from our pale blue dot. And yet, here is what I keep coming back to. Here is what feels, to me, like the most important idea in this entire video. The universe did not have to allow us anything. Think about that. There is no law of logic that requires a universe to exist. There is no principle that says, if a universe exists, it must be one where stars burn long enough for planets to form. There is no requirement that chemistry must allow the self-replication and mutation that produces evolution. There is no rule that evolution must eventually produce consciousness, beings capable of knowing that they exist. And then, in this particular moment of cosmic history, on this particular rocky planet orbiting this particular middle-aged yellow star in the outer suburbs of this particular galaxy, that physical process produced beings who could look back at it and understand it. Who could calculate the size of the universe from a bedroom? Who could determine the fate of the cosmos from a laboratory? Who could feel awe at the fact of their own existence? That, to me, is not a tragedy. That is something closer to a miracle. No hint that help will come from elsewhere. He was saying, the walls are real. The universe is not coming to rescue us. The cavalry is not over that horizon. What we are on our own. The earth is where we make our stand. That's not defeat. That's dignity. The walls tell us, this is your stand. This is your stage. Not the whole universe. Not the 2 trillion galaxies spinning in the dark. Not the superclusters stretching across billions of light years. Not the infinite future after the stars go out. This solar system, this galaxy, this local group, this 100 trillion year window. This is where you make your stand. Don't squander it looking for a bigger stage. This stage is enough. More than enough. The farthest humanity will ever travel ends at a wall we can see, a wall we can calculate, a wall that was always there even before we knew it. But inside that wall, between here and that horizon, there is room for 10,000 civilizations, 100 trillion years of starlight, and an amount of wonder that exceeds anything we have so far imagined. We have not been handed infinity. We have been handed enough. And what we do with enough, whether we treat our bounded cosmic home with the reverence it deserves, whether we use the window we have while it's open, whether we build something beautiful within these walls, that is the only question that has ever actually mattered. You started this video on Earth, and you still are on Earth. Nothing has moved. But I hope the Earth feels different now. I hope the sky outside your window looks different. I hope the next time you see a star, one of those photons that traveled for years or thousands of years to touch your eye, you feel something of what I feel when I think about all of this. We are not at the beginning of a story that reaches all 2 trillion galaxies. We are at the beginning of a story that reaches all the reachable ones, the 3 million within our horizon, and most importantly, the local group that gravity has reserved for us, the cosmic home that will remain ours while the rest of the universe recedes. It is a smaller story than some people want. It is a real story. It is our story. I want to know what landed for you in this video. What moment hit differently? Drop it in the comments. And if you haven't yet, subscribe, because this is the kind of thing I'm going to keep making. Questions that don't fully resolve. Ideas that rearrange the furniture in your mind. The biggest questions the universe is quietly asking all of us. Thank you for watching. Thank you for your curiosity. Thank you for spending 3.5 hours with the hardest, most important, most beautiful questions I know. The wall is there. The wall defines you. And inside it, you are free.